Welcome to the third screencast of the electrokinetics module. Now we have covered the Butler-Volmer equation, we can move towards more complex electrocatalytic mechanisms and also discuss the corresponding Tafel slopes. For this, I would recommend you to start with quiz question 3.5. Before diving into the equations again, I first would like to discuss what makes a good electrocatalyst, because it's the electrocatalyst that determines whether a reaction is fast or slow. It is the electrocatalyst that determines whether a reaction has a high or a low exchange current density. Now, whether something is a good electrocatalyst really depends on the properties of the metal, because most electrocatalysts are metals, although you can also have, for example, oxides as electrocatalysts. Here I give the example of hydrogen evolution. You can see here that this process can take place in two steps. The first step, a proton binds to the surface, forming a bonded hydrogen atom, and then later two hydrogen atoms combine to give a hydrogen molecule. Now, here you can see the exchange current densities as have been reported for hydrogen evolution. And you can see that there's a huge variation because this is a logarithmic axis. So for example, on a metal like cadmium, the exchange current density is only 10 to the minus 9 amps per square centimeter. Whereas on a metal like platinum, the exchange current density is 10 to the minus 3 amps per square centimeter. So what do we see? We see here an interesting relation between the exchange current density and the bond strength of the metal hydrogen bond. And molecules that bind the metals that bind the hydrogen only weakly, like cadmium again, do not result in a high exchange current density. The same applies to metals that bind the hydrogen very strongly, like titanium. You need apparently a good balance. It should not bind too weak, it shouldn't bind too strong. And then actually that makes quite a lot of sense, because if it binds very weakly, yeah, then this first step does not occur. On the other hand, if it binds too strong, then the second step will not occur because the hydrogen are sitting happily on the surface and nothing happens. So you need this right binding strength for the reaction to occur. So now that is obviously very catalyst dependent. It also strongly depends on the reaction and on the intermediate. So platinum is a good catalyst for hydrogen evolution, but that does not necessarily make it a good electrocatalyst for all reactions. There's a second property that also determines whether a material is a good electrocatalyst. That one is a lot simpler. Namely, it's the surface roughness. The more surface area you have, the more electrocatalytic area you have for the reaction. And since we normally in electrochemistry we plot current densities based on the geometric area, not on the real area, a material that has a very high surface roughness has a higher electrocatalytic activity than a material with a low surface roughness. You can see here two materials, very high surface roughness, very low surface roughness. So this material, at least if the electrocatalytic properties would be the same, for example, if this would be platinum and that would also be platinum, then this one would have a much higher exchange current density, just because we list the exchange current density based on the geometric area. So it also means that the simple strategy to improve your electrocatalyst is just by increasing the surface area. Now, let's continue with the equations. What we have discussed before were all equations that covered a single electron transfer. That's what we covered in module 3.2, the Butler-Volmer equation. That's an equation that applies to a single electron transfer. But basically any reaction is more complex. It involves electrochemical steps, often it also involves chemical steps, and it's the combination of these reactions that in the end determine the total kinetic rate of the reaction. Now, we will now derive what happens for such a multi-step mechanism, but first let's take a look at some of the relevant equations we again need, and we can still take from section 3.2, namely this equation. The current density depends on the rate constant, the concentration, and the N and the F, and the equation for the rate constant, which is K0 with this E power, with the alpha in it, and the difference between the potential and the standard equilibrium potential. And for that, as said, we discussed, it's about 120 or 180 millivolt per decade. So that was standard. Okay, on the next slide, we're moving towards a complex reaction. And this complex reaction is the reduction of zinc 2 plus to zinc, as shown here. This is a two-step reaction. Namely, you first have the reduction of zinc 2 plus electron gives zinc plus, and then you have the reaction of zinc plus electron gives zinc. It's very rare that two electrons are transferred at the same time. So this is a two-step mechanism. Now the question is, which one is the rate determining step? Now, on this slide we will assume that the rate determining step is the first step, namely the reduction of zinc 2 plus to zinc. Now, what does that mean in sense of equations? So the rate determining step, as we can see here, is this first reaction. So we need the rate constant of that reaction multiplied by the concentration of zinc 2 plus, because we're looking at this reaction, the first reaction. Now, next, we can then in that reaction introduce the electrochemical kinetics, as we shown on the previous slide and also in section 3.2. So we introduce the K0 and the potential minus the standard electrode potential multiplied by the concentration. So then we bring that to the current density. Now we see a small difference with what we previously saw, and namely that is that now suddenly, because every zinc plus that we form immediately reacts further to zinc, because this is the rate determining step, which means that the following step is fast. So for every zinc plus we form, we immediately form the zinc, which means we use 2 electrons. So that's here why the 2 shows up. And then the equation suddenly has a 2 in front of the exchange current density. Now, is that a big deal? No, basically it's not. Because where does this 2 end up? This 2 ends up here. There it basically does not have any effect. It basically gives you the impression that the exchange current density is twice as high, which is not the case. But most importantly, if you measure the Tafel slope of this reaction, you will still measure that the dependence of the potential on the log of the current density is 2.3 multiplied by R multiplied by T divided by alpha and F, which is still 120 millivolts per decade. So what can we say from this? A Tafel slope of 120 millivolts per decade is typical of an electrochemical process in which the first electron transfer is rate determining. And if that is the case, it basically doesn't matter which reactions come afterwards. Then the Tafel slope will always be 120 millivolts per decade. Now let's look at the second possible mechanism, and that is that not the first step is rate determining, the formation of Zn plus, but the second step is rate determining, namely the formation of zinc. This means that the first step is then at equilibrium. Now, what does that mean for the equations? It becomes a bit more complex. We can now the rate determining step can be written like this. R is K multiplied by the concentration of zinc plus, because this is the step we are studying. But we don't know the concentration of zinc plus in solution. That's not given. So we have to calculate that. And that we can calculate using the Nernst equation. Because the first reaction, as said, is in equilibrium. As long as it's not rate determining, which is not. So then we can write down this equation. The equilibrium potential is the standard electrode potential plus this. And this we can rewrite to the concentration of zinc plus is the concentration of zinc 2 plus with this E power where we have Fr or T and E minus EE0. And this we can now start introducing into our electrochemical kinetics term, because here we have the concentration of Zn plus, and now we can insert this equation. And you see that coming back here. But we also have to introduce the normal kinetics into that with the K0 for the second reaction, and also with the term with the alpha again and the E minus EE0. So we have now these two E powers, and the nice thing about E powers is that you can add them together. So it's relatively straightforward to then come to this equation where R is K0, E, and now we see alpha plus 1 turning, and the 1 is coming from this part. So the plus 1 turns up here, multiplied by the concentration of zinc 2 plus. Now, then we convert again to the current density. Again, we have this 2, just like as is in the previous case. But now we again here see still this alpha and C plus 1. And now, if we now turn that to a Tafel slope, so divide the eta dividing by the log of the I, then we see that now suddenly we have here 2.3 RT divided by alpha plus 1 multiplied by F. And this is about 40 millivolts per decade. And that makes sense because alpha is normally 0.5, no more or less. If you add 1 to that, it's basically this term is 3 times larger. So instead of 120 millivolts, you get about 40 millivolts. Now, what is the important conclusion from this that you can derive is that for this type of mechanism, which we call an EE star mechanism, an electrochemical equilibrium followed by an electrochemical rate determining step, you always get a Tafel slope of 40 millivolts. Depending, of course, on the alphas, but assuming that alpha is 0.5, it's kind of independent of the reaction. You should always get this Tafel slope of about 40 millivolt. Okay. Well, I could have continued with more of these equations and derivations, but I guess you're already a bit tired of them. And as said on the previous slide, they are kind of universally applicable, which also means that other people have already done these derivations for you. And that you can see here basically in this overview table. So what we saw for E star, the Tafel slope is 2.3 RT alpha F, resulting in about 120. The one we showed also the EE star, so the second electrochemical step rate determining, that results in this equation and a value of 40 millivolt per decade. But there are more options. For example, an electrochemical equilibrium followed by a chemical rate determining step. Then you get this as a result, with a Tafel slope of 60. And there are another possibilities. Two electrochemical equilibria followed by a chemical rate determining step. Now, then you get this as a result. And that is 30 millivolts per decade. And then here you see another one, ECE star. So an electrochemical equilibrium followed by a chemical equilibrium followed by an electrochemical rate determining step. And that is then results in this. Again 40. So you see actually these one are the same. The EE star and the ECE star, that's the same. Well, basically this C does not really matter. And what is also important to notice is that all the reactions that are after the star, so for example E star E is the same as an E star. So the reactions after the rate determining step, they do not matter. So this is very nice information, because now we can look at our electrochemical experiments, measure the Tafel slopes, and from this we can say something about the mechanisms. And sometimes it really allows you to make strong conclusions on, for example, the intermediates of a reaction. Often reactions are so complex that you need other techniques to further support your hypothesis for a mechanism. Now, let's play around a bit with Tafel slopes, and for this I would recommend you to carry out question 3 quiz question 3.6. Well, this brings us to the end of this screencast and also to the end of module 3 on electrokinetics, where we have covered a lot of fundamentals on it. But most importantly, you have learned about the Butler-Volmer equation, which you can use to determine overpotentials as a function of current density. And for that you need the exchange current density and the Tafel slope. And that's the other important lesson that you should have learned, is that you can use Tafel slopes to say something about the mechanism of a reaction. And this is where I would like to conclude this module. I would like to thank you for your attention.